So hello everybody. So welcome to this new discourse series. So I'm Fatma Takibi. I'm the co-chair of the Junior Members Working Group, and please meet with my colleague Gaël.
So hello, my name is Gaël Bulgen. I'll be the second moderator of this talk. I work at the Institute, the Observatory of Geneva, where I'm a postdoc, and I'm also a member of the executive committee of the Junior Members Working Group. But before starting with the discourse that you've been all waiting for, we have a short announcement that has to be made by our colleague Camilla, that is here about the IAU logo contest.
Hello, everyone. So I will finally announce the winner of the logo competition. Thanks for everyone that participated of all of your votes. We had many logo submissions and we also had many votes. So I am gonna share my screen. Which I guess is this one. Yes. And there we are. So back in January, we announced this new activity. We wanted a logo that could represent our working group, that could be used in different activities. So as I said, we had many submissions, and the winner of the logo competition is, we have Katharina Himmer that won. She is a postdoc researcher in Leiden Observatory in Leiden University, and she works in the Allegro Alma ARC node. So you'll see this logo appearing everywhere from now on, and please share it. And I just leave the floor to Katharina, that she's gonna explain the creation process of this kind of logo. Katharina, the floor is yours.
Hi, hello everyone. Very happy to hear that I won, and thank you all for your votes. When I saw this competition, I thought, oh, that must be fun to participate. And to gather ideas, I looked at the description of the Junior Member Working Group on the web, and the first goal that is given there is, it says that we want to build a network of early career researchers locally, nationally, and internationally. And that's kind of what I based this logo on. So that, you know, the arms together go together to build a network. And then they're kind of on a circle, so which represents the world. And then the arms that go to the sides is kind of like, you know, putting the arm on your friend, for this kind of represents inclusion and support of your fellow junior members. And then of course stars, because, you know, astronomy.
It's really great. It's really, really great. It represents very well our working group. So thank you very much for participating. And again, congratulations. So at the moment, we leave the floor back again to Fatoumata and Gaël and Olivier.
So again, welcome everyone. So as you can see, we have Olivier Hainaut with us. He will speak about satellite mega-constellations and astronomy, a phantom menace or a new hope. So a brief presentation of Olivier. He's an astronomer at ESO and has gained substantial experience in telescope and observatory operations. He has led the ESO VLT and before that the La Silla science operations. He was a support astronomer on La Silla, starting as a PhD student and a Belgian civil service cooperant. And he was also a postdoc at the University of Hawaii, where he spent many nights on the Mauna Kea. So now he's working at the ESO headquarters, working on the integration of the next ELT, next generation ELT operations with other telescopes. And he's originally a specialist of comets and asteroid observations, and he's been involved in astronomical ground support and also various space missions. So Olivier, it's a real pleasure to have you here. And so the talk will be about 30 minutes with 30 minutes discussions. And of course, for the attendees, you can use the Q&A in the Zoom, the chat on YouTube. And if we run out of time to answer the questions, we'll take note of them and try to answer them in writing. So again, Olivier, our pleasure to have you here. And please take it away.
Thank you. Thanks a lot for the invitation and for the opportunity. And I'll try to share my screen. And here we go. You should see it coming. Yep. Okay, so I'm going to talk about satellite constellations and their effect on ground-based astronomy. And this is a work that I present on behalf of the ESO working group on satellites, which is growing and include astronomers and atmosphere scientists and specialists in external relations, which you'll see will be useful. So let me start just a few words on my background. So as Gael said, I'm an astronomer. I specialize in minor bodies in the solar system, and over the years I like weird minor bodies, so comets, asteroids, and especially those that are misbehaving and that have weird cases of cometary activity. So bottom left, you should see my mouse, I guess, yes. Bottom left is a comet, it's an asteroid that is crumbling and falling in pieces. And this bottom right is a small asteroid that has been hit by another one, and we can actually see the effects. So it's kind of fun objects. And maybe you recognize Oumuamua. I was lucky enough to be part of the study of that object. Okay, in terms of my study, as Gael said, I started in Liège, and then I moved to La Silla as a civil service, which in that time, last millennium, was a very nice way to avoid military service, doing something really interesting. So I managed to get my hands on all the telescopes on La Silla. And I came back to Europe to complete my PhD and moved immediately to Hawaii, at the University of Hawaii. And so that means that I could get my hands on all the telescopes on Mauna Kea, which is also great. Then I moved back to La Silla, where I was eventually put in charge of the NTT, then the observatory as a whole. And finally, I moved to Paranal, which was fantastic. It's the greatest, nicest telescope you can dream of. It's really fantastic. Now I'm back in Garching at headquarters, and I'm trying to make sure that when the ELT, the next big telescope, comes on sky, we can operate it. So, satellites, mega-constellation. It all started on the 24th of May 2019, almost 2 years ago, when Starlink launched the first batch of 60 satellites. That was spectacular. I don't know if some of you have seen the first train. It was really completely science fiction. You would see these 60 bright spots, really bright, moving super fast together as a train in the sky. So the first reaction was, wow, okay, this is really science fiction coming through. Second reaction was, well, kind of frightening, especially when we realized that Elon Musk was planning to send 12,000 of these satellites. If you see the effect of 60, if you scale to 12,000, it starts to be worrisome. And so we also had early results, images that were affected by satellites, and affected is really an understatement. It can be dramatic. So would the sky that we know like this turn out to be like that? So there was a moment of panic. Then we decided, okay, let's first try to understand what it really means. So first, how many satellites? So Telecom Mega-Constellations, they need many. So why? Because their goal is to have telecommunication with low latency. And low latency, that implies low altitude. And they want complete global coverage together with the low altitude, that implies that you need really many satellites, thousands. So the way these satellites are put in the sky, they are assembled on shells using the Valker configuration. You have one example on the left. This is one of the Valker shells for the Starlink constellation. One shell is typically of the order of 1,000 satellites on several tens of planes, and on each plane you have several tens of satellites. And the inclination of the orbit decides how far you go to the pole. So one full constellation will be an ensemble, a collection of these shells to get the best possible coverage of the regions of interest. So how many? The table on the left shows you the constellations that are known of. So some of them have already filed their application, some of them have already launched satellites, some of them are just projects. So there are about 30 sub-constellations for a total of 96,000 satellites. That's a lot. Today, about 1,300 of these satellites have been launched, most of them by Starlink, some of them by OneWeb. Of these constellations, some of them have not filed their application yet. Others did, but they withdrew their application. OneWeb, which is one of the big one, actually filed for bankruptcy and then was revived. And then they decided to downscale their constellation from 50,000 to 6,300 satellites. So you have to take these numbers with a grain of salt. Historically, many companies file applications, but actually many do not launch anything. Many because they die, they bankrupt, others because they change their mind. Another important thing is that there are many non-telecommunication constellations for teledetection, for example. But most of these are much smaller satellites, CubeSats of a few kilo. So that they are not really relevant for astronomy, but they still contribute to orbital crowding. Okay, so we have all these numbers and we have the specifications of the constellations, so we can start to do some simulations. First thing is to try to see how many satellites are in sight. And okay, here you have on the right a simulation of the Starlink satellites with an observatory at the top of the Earth. And of all these dots, each of them is a satellite. Only those that are above the horizon would be visible. So I painted them in blue. And actually for astronomical observations, we tend not to observe close to the horizon. So only those above an elevation of 30 degrees would be relevant. And if you see, this is a view of the sky above the observatory. Each dot is a satellite. You see that most of them are close to the horizon. It's simply because when you look close to the horizon, you go through a much thicker fraction of the constellation that if you look at zenith. So about 90% of the satellites are above, are below 30 degrees, and only 10% of those inside are above 30 degrees. And if you take the total of the constellation, it's about 5% above the horizon and 10 times less, 0.5% above 30 degrees. So if we have 100,000 satellites, that's still 5,000 above the horizon and 500 in the region of interest for astronomers. The second thing is that to be visible, a satellite must be above the horizon, but it also must be illuminated by the sun. So there is a small time during which the satellite is still illuminated while it's already night at the observatory. And as the sun goes down, the satellite will will fall into the shadow and will not be visible anymore. So we can do simulations for all kinds of constellations, different observatories, etc. And this is a plot that summarizes the result. This is for Paranal, but the plot would look fairly similar for other regions. So in X is the time of the night, so sunset, midnight, and sunrise. The left part of the plot is for a winter night. The right part of the plot is for summer night. As the plots are symmetric, I chopped so to be able to show both at the same time. Top part is all the satellites that are above the horizon. And you see that we have about 1,900 satellites above the horizon. This is considering that the full Starlink and the full OneWeb constellation have been launched. So we're talking late 2027. And as the sun goes down, those that are above the horizon but illuminated, their number goes down eventually to 0 in winter, but not 0 in summer. So in terms of visual observations, I focus now to those that are above 10 degrees above the horizon. Normally you really can't see anything below 10 degrees. And that's about 800 satellites. But only a fraction of them will be visible with naked eye. And using Starlink as a model, the others might be different, but we have a characterization of Starlink. That means that at the end of twilight in winter, there would be 0 satellites visible. But in summer, we could have of the order of 10 satellites even at midnight, 10 satellites over the whole sky. And this is for a magnitude brighter than 5. So that means that they would be visible, but most of them would be close to magnitude 5. And finally, for astronomy, I now focus to above 30 degrees in the lower panel. We have about 200 satellites in the sky. And at the end of twilight in summer, 150 would still be illuminated and 16 in the middle of the night in summer. That number goes down to 0 a few hours after sunset in winter. So this gives us roughly the numbers of what we can expect. If I generalize this to all the constellations we know about, this is again in X, the elevation of the sun below the horizon. So sunset is here, end of twilight is where the blue stops. This is the dark, This is the dark night, and the night ends at midnight, which falls at different elevations depending on the season. And you see that the Starlink satellites are much more numerous than the OneWeb ones. However, because they are on a much lower altitude, we see less and they vanish sooner in the shadow. The OneWeb ones are less numerous, but that as they are higher, they are much more annoying, and actually they can be visible during the whole night in summer. And if you look at another constellation, the Samsung ones, they are even higher. And so that means that they will be visible deeper into the night. The thick black line gives you the total number, so totaling at about a few hundreds during the day. So to summarize the question, how many? In orbit, before the constellations were launched, there were about 2,800 low Earth orbit satellites. Today, with those that have already been launched, about 1,400. So that means we have just about 4,000 satellites. When the full Starlink and OneWeb will be completed, we expect 50,000. And if we accumulate everything that is described on paper, we would have 60,000 or more. Now, remember, that's really rule of thumb is 5% is above the horizon, and 10 times less, 0.5% above 30 degrees of elevation. And in terms of visible ones by naked eye, we're talking about a few tens at twilight and about 10 at midnight in summer. There will be some additional mitigation, I'll talk about that later, to make them less bright. So these numbers will be actually smaller. So first, we can be reassured. The claim that there would be more satellites than stars is fortunately not true. However, even the much fainter ones have an effect on astronomical observations. So I won't go into the details, but it's actually quite simple. We can model the position and the velocity of these satellites. So to see how many we have in an observation, we do the simulation, then we count how many we have in the field of view instantaneously. And of course, that scales with the size of the field of view. But as these move very fast, we're talking about tens of degrees per minute, you have to take into account the trailing and how many satellites will move in and out of the field of view. So there is this formula, the number of trail is the area of the field of view multiplied by a density plus the size of the field of view times the exposure time times a density of trail, and we can model this. So looking at the results, okay, this is a busy table, but basically you can look only at the colors. In X is again the elevation of the sun, so sunset, twilight in blue and dark night in white. And each line is an observation technique. So the first one is classic imaging. And the line tells you how many trails you would get in an image. So on average here, you would get 0.16 trail per 5-minute image with that instrument. So that means that on roughly one exposure out of 6 would be would have a satellite trail. Now, I color coded these numbers depending on the effect, because it's not a trail can be more damaging or less damaging depending on the technique. Green is less than 0.1% of damaged science exposure. So basically, it's in the noise. The dirty gray is less than 1%, which means noticeable, but probably still okay. The yellow one is less than 3%, and 3% is a good rule of thumb. It's the downtime that we accept, the technical downtime that we accept from our telescopes. So if the satellites reach 3%, that means that basically all our downtime budget is exhausted. Red is up to 30%, so that's really bad. And then there is a dark purple red. This is more than 30% of the frame, so that's basically unusable. So summary number one is that most of the observations will be damaged around twilight, just before, just after, and deeper into the night, we are essentially okay, except for ultra-wide field imaging, because of the ultra-wide field, especially on a large telescope like LSST, Vera Rubin, they would be affected at a noticeable level during a good fraction of the night. And in particular, the bright satellites have a very nasty effect on the Vera Rubin observatory, and all exposures during nautical twilight are going to be ruined, and a good fraction of them also after astronomical twilight. So now I switch gear to radio astronomy. So first, disclaimer, I'm not a radio astronomer. For radio astronomy, the situation is quite different. The satellites are emitting, so they are visible 24 hours. They don't disappear when they fall into the shadow. There is also something nasty about the laws of physics with antenna, is the concept of side lobes. So on top left, you see a radio telescope pointing at a satellite and the satellite pointing at the telescope. So it's clear that there it will be a very bright detection. Fortunately, because the beams are fairly narrow, this is extremely unlikely. I'm talking fraction of a percent. However, you have side lobes, and if the side lobe of the antenna looks straight into the main lobe of the satellite, or if the main lobe of the telescope looks into one of the side lobe of the satellite, there will be a detection. And even though there is a strong attenuation, it's going to contribute. And finally, you can have interaction side lobe to side lobe. And because of the number of satellites, that is going to be extremely frequent. But the attenuation of the side lobes is very strong. So an individual satellite will not be detected. However, if you have hundreds of satellites, they would possibly contribute to the noise. Back of the envelope calculation, it should be okay, but should be okay is too close. So there are some more studies being done to really study what will be the effect. So another effect of the law of physics and engineering is frequency bleeding. So even if a satellite is emitting only at a given frequency, frequencies on the side will also have some signal. Good engineering helps, but there are some limits. Traditionally, radio telescope would move to radio quiet areas, for example, northern Chile in the Atacama Desert. And that works well to protect from ground pollution. But for satellites, of course, it does not work because they go all over the Earth. So that's also bad. There are some positive points. First, radio frequencies are very heavily regulated, and we, the astronomers, have some frequency bands that are protected. Of course, because of redshift, some of our objects emit outside of these protected regions, and so that means that we might be affected. You see that I marked some of these with little green stars. These we can mitigate by negotiating with the satellite operators that they don't point their beams directly to the telescopes. So there is hope on that side. So overall, the satellite will impact the whole astronomy ecosystem. Some time-critical observations will be affected, just bad luck, but as they are time-critical, they cannot be replaced. Something really nasty is the contamination of spectra. If you have an image, it's pretty obvious to see if there is a trail going across it. However, for a spectrum, it's much more difficult, and we might detect it only at the time of analyzing the data. The wide field telescopes will be heavily affected, and that means that some surveys, for example, those that focus on twilight observation or near Earth objects, will be really affected. And also, the surveys are feeders for other telescopes. They detect objects. And so that means that if they miss some of these detections, the whole ecosystem of the other telescopes will also be impacted. On the radio side, it's another erosion to our access to the radio spectrum that we need to take care of. Something else that is really not my field is the problem of orbital crowding. If you pack more satellites in low Earth orbit, there will be some space traffic issues, and collision avoidance is going to become more complicated. So Starlink, for example, has an extremely advanced and powerful collision avoidance system, but we hope that the others will be as good, because a collision would potentially make a whole shell, a whole orbit unusable. So the bottom plots show the number of objects in low Earth orbit, small one on the left, bigger one on the right, over time. It stops in 2020, and you see the blue part here is the launch of Starlink. Today, we would be at 2000, which is about here on that scale. So let's start to talk about mitigation. I'll mention several levels of mitigations, but everything starts with the astronomical community. We were caught by surprise, and it's our fault because everything had been published and documented. So we could have started this years ago. We did not. No, we did. So there have been study simulations, observation campaigns, and a good summary is the briefing to the ESO Council. This is a link, a short link, where you can get the document. We also needed to understand what we can do about mitigation. And there are several ways. Scheduling tools. We know where the satellite density is the lowest, so we can wait for our astronomical object to be in that region to observe it. We can also do shuttering with a field of view camera monitoring the field of view. We can spot when a satellite would cross the field of view, close the shutter, let it go through and reopen the shutter. As the satellites move very fast, that would be just a few seconds. Talking with the satellite operator, we can also hope to darken the satellite. I'll say more about that. And you've seen that the altitude of the satellite is an issue, so it's good to keep them low. And radio astronomy community is also doing some work. So something important to keep in mind is that even combining all these mitigation techniques, we will not be able to avoid all impacts. So let me skip a few slides and go straight to the Starlink mitigation. So at the beginning, there was an outcry, the astronomers saying, oh, Elon Musk is going to ruin astronomy. And actually, they were extremely responsive. Once we contacted them, they said, okay, give us specifications. And one of the problems that was the super bright string of pearls. They are really beautiful, but they are really ruining the night sky. And that they have solved simply by changing the attitude, the orientation of the satellite during the low orbit phase, so that the small edge of the satellite is pointing toward the sun. So that means that just by doing that, they went 3 to 5 magnitude fainter. So that means that if you have not seen the early strings of pearls, too bad, because nowadays the Starlink satellites are not that spectacular anymore, which is good for astrophotography. Another issue is that we really need the satellites to be fainter than magnitude 7, because they would not be visible with naked eye, but also it's a good benchmark, because that is the magnitude that saturates the Vera Rubin observatory. So something that Starlink has done is essentially paint their satellite in black and to make it darker. And there have been some measurements. Hi, Jeremy. There have been some measurements of the dark sat that showed that the satellite is about twice fainter in the visible, little bit less in the infrared. So that's not sufficient for us. And also it causes problems with the thermal control of the satellite. So Starlink abandoned that. Something that they did is another extremely simple adjustment, which is to change the orientation of the solar panel so that when it is illuminated, the illuminated side is not visible from the ground. So it's much darker. And finally, they introduced the visor sat. So essentially, the deployed sunshades. You see them here on this view, and they are placed in such way that they cast a shadow on the bright part of the satellite. And so that means that the bright part of the most reflective part of the satellite are not illuminated, so they are not visible anymore. And there it's about a factor 3 fainter, which means that it's just about at magnitude 7 at zenith. So we are getting there. All the satellites launched since mid-2020 have some visors, and SpaceX is iterating with their design. So Elon Musk said no impact whatsoever and will take corrective action if above 0. And I have to say that until now, it is true. They have been extremely responsive. And when we give their engineers some specifications, they engage and they find solutions. So I think that the contact with Starlink is really good and they're extremely reactive. And that has a very strong impact on the others. So since that, OneWeb and now Amazon Kuiper and some others are also in discussion with the astronomers to refine their design and improve their design. So our strategy now is to engage and to keep developing the awareness. And we hope that with these early players, we can develop a set of best practices that the others will utilize. Simply because it's better, it's actually in some cases cheaper, and so that means that it's really a win-win. We have no way to force them to do that, so it's really just by talking and finding solutions that we hope to reach this. Indeed, we have a huge challenge, is that there is no regulation for visible and infrared light in the sky. In radio, there is a very powerful spectrum management. It's not sufficient, but there is something, while in the visible and in the infrared, there is nothing. And so that opens some broader question. Who owns the sky? Who has the right to the night sky, and who decides? And also, there are some, we need to reach a balance between sky for science and sky for other purposes. And so I will end with this slide here, which shows the coverage of Starlink today. And you see basically where there are some dots, they have coverage. Coverage in the equator is still about 50% of the time. In Europe, it's now 95% of the time. And for example, you can give good internet to remote communities, so places where there's no cable and no cell phone. In terms of safety, the airlines would have real-time telemetry, so no more hunting for black boxes in case of an accident. Same also for the ships at sea who currently rely on radio or high latency internet. Now they would have much better access. And there are also other things like environment. You could put a Starlink antenna in the most remote place and access your remote sensor data, volcano, desert, forests, whatever. You can also give access to villages in the middle of nowhere. People have said, it's too expensive. Well, actually, it's $500 for the time being, assuming that the Starlink sells it. But that can be a whole village. So there is really hope that remote communities will be connected. Something that is also interesting is that these constellations will give alternate internet access. Currently, internet comes from my phone cable or my television cable or my satellite. So basically, it's in my case, it's Deutsche Telekom. There are a few others, but it's always Germany. With the constellations, this means that there are some independent providers. Starlink is American, OneWeb is British, Samsung is Korean. So that means that restricting access to internet will be much more difficult. And I suspect that some regimes are not extremely happy because the great firewalls will not work anymore. So the way ahead, we see it as shared stewardship. Together, the astronomy community, the society, and the satellite operator, we hope to continue to encourage all the actors to collaborate and to set up some rules and to share information. And eventually, we hope to have some national regulatory processes that considers us the astronomers, but international agreements and laws take forever. So that means that we cannot wait for that. We need to engage with the satellites operator now. And here I just put the links of some interesting summaries. The first one is probably the shortest and most complete. The others are bigger. And that's all I have. I leave the slide a few more seconds and then unshare so that you can see me when I talk.
So first, thank you very much for your very nice talk. I can see that we already have a live question. So one thing that from one of the questions we had, so you mentioned that so far all the industry actors were really engaging and listening to what you had to say regarding your concerns about the quality of the night sky, etc., etc. What would you do if, for example, one of these actors was not really cooperative? What kind of leverage do you have? Because so far it worked, right? You could engage them.
We have zero legal leverage because all these constellations have to file applications, and these are controlled by space treaties, which are in turn controlled by national laws, and they have to adhere to that. But that does not consider optical astronomy. So the only thing we can do is set up best practices, and the fact that the second and third operators are following these best practices already is encouraging. Especially there will be some technological solutions developed by the first ones that can be reused by the others. But to set up a treaty like the one in radio astronomy, the one for radio communication, you have to take into account 10 years. So that means that it's going to be way too late. We really need to move now.
Does it mean also that we should have moved earlier?
Well, yes, definitely. No, seriously. I mean, all the applications were known, and just we never realized. Also, another thing. There might be Elon Musk effect in the sense that the first constellation was launched with an attitude, a positioning designed to make it as bright as possible. So they really wanted to advertise it, and it worked, and it was super cool. Just that it basically we were aware from there on. Now. Currently, there are 3 trains in the sky, and I bet nobody has seen them because they're really faint and hard to see. So if they had done that from the beginning, we would probably still not have noticed. So it's good that Elon Musk loves to brag.
So So thank you so much for these answers. And other questions, what kind of tools, strategies should the astronomical observatories develop to cope with future and current satellite constellations?
Okay, well, there are really a series of tools. The first one is know your enemy. So we need to have real-time maps of the satellite density. To keep track of the individual satellite is complicated, but to know on average where they are, that's really simple. And so that means that there are regions in the sky where the density of satellite is much lower. So if you observe there, the probability that you get affected can be a factor of 10 lower than if you observe somewhere else. So just by using these sky maps together with the scheduling of the observation, we can gain a lot. Another thing is a more active control. We could mount a small camera on top of our telescope, looking at the same field of view and detecting the satellites in real time. And when one of them approaches the science field of view, we just close the shutter, let the satellite go through, and reopen the shutter when it's gone. We have this kind of technology already for our lasers. You know that some of our lasers have are quite powerful. Actually, we are talking about 10-watt lasers, which is a lot. And so we have airplane detection systems that shut down the laser in order not to fry the pilot's eye if they happen to look into the beam. There are also some software techniques. The brightest satellites are really difficult to subtract from the data, but the faintest one, we can deal with that, and we are working on algorithms that would remove the satellite trails from the data. So all kinds of developments in terms of the knowing where the satellites are. OneWeb and Starlink have already agreed to publish their orbital elements in real time. Actually, they do it already, but they agreed to publish super accurate orbital elements so that we would know where the satellites are with a precision sufficient to know if they fall into the slit of a spectrograph.
But is it going to be expensive for the observatories to develop all of these tools?
Yeah, yes, no, we'll define expenses. I mean, the hardware for a real-time satellite detection camera, we're probably talking about a few 10,000 euros plus some development. So is that expensive? Is that cheap? I don't know. The ELT, the cost of the ELT is 1 billion. So to add even 50,000 euros more is nothing. For a small observatory, 50,000 euros might be more expensive, but there are already some commercial companies that are offering things that would probably not be good enough for the ELT, but that might be good enough for a small observatory or an amateur observatory.
Thank you.
Now, in terms of, there were some questions, well, let's sue the satellite companies. Well, first of all, we have to prove damage. And second, we have to evaluate it. And if we get really, really lucky after years of litigations, we could get a few millions. Starlink has already invested several millions in their mitigation. Just the DarkSat experiment, basically they sacrificed one of their satellites. They knew it wouldn't work just to do the test. And the changes of the VisorSat is also in terms of millions, in terms of design chain and production chain. So it's really better that we continue to negotiate because there is actually some goodwill. And while if we would start suing these companies, they are certainly better in terms of lawyers than we are.
Yeah.
That is certain. So one live question. Someone thanking you for your reassuring talk. And the question is, are there some quantitative simulations regarding the impact on SKA observations?
Yes, there are. And as I said in the slide, I'm not a radio astronomer, and I follow that not as closely as I should, maybe. But yes, there are some simulations. They're not ready yet, I think, because they are much, much more complicated than what I did for the visible. In the visible, the first simulations were really back of the envelope. I mean, literally. The second set of simulations were an Excel sheet. So now we have a few thousands of lines of Python, so it's moving a little bit more towards professional. But in terms of the physics involved for radio astronomy, it's much more complicated, so it takes time.
Other questions, did the satellite constellations have an impact on your research work?
Okay, today there are 1,400 satellites from these constellations, while there are, in terms of visible satellites, about twice that in low Earth orbit and 3 times that in total. So that means that right now there are still a small contribution to the satellite issue. They're not a problem yet. They're growing rapidly. I mean, launching 60 satellites a week, that counts. But today, I would say that satellites are an annoyance. I've had some exposure ruined by satellites, but personally, in my whole career, it's probably 10.
Okay, and so there's a comment maybe linked to that. There may be a hidden cost in years of PhD student effort and postdoc effort spent working out mitigations and software fixes.
First of all, developing software is good for graduate students. So, no, more seriously, yes, there is a cost. Okay, and someone said in the questions, this is a reassuring talk. It's not meant to be reassuring. It's meant to be realistic. And there was a lot of panic at the beginning. There is no reason to panic, but we have an issue. And some telescopes like the Vera Rubin are going to be affected. And yes, there will be some cost. So software, but also hardware. For example, the Vera Rubin camera has a very stupid way to react to saturating trails. And I suspect that if they had built the camera knowing that they might have tried to build it in a different way. So that means that there will be some research and development, some costs, but that's an investment. We will learn how to subtract all kinds of horrors from our data. So, and the other thing is we do not own the sky. We are the guardian of the night sky, but we don't own it. And the civil society, I mean, the non-astronomers have also the right to use it, either for their enjoyment, to watch the, to have a non-polluted sky, and but also to use it. I personally believe that to have global internet is going to be better than having no global internet.
Thanks a lot.
So bouncing back on that, what would be your arguments if you had to reply to someone saying that actually these satellites, these constellations have a direct impact on society? While when we talk about astronomy, we talk about research, we talk about the night sky, etc. We play on a longer time scale, and the trickle-down effect might take a longer time, and this does not have the same direct implication than these satellites. How would you? What kind of arguments would you use?
It's really it's the same as all the debate about fundamental research versus direct applied research or engineering. You need both. And these satellites would not have been possible if we had not mastered celestial mechanics all the way to general relativity. Without celestial mechanics and general relativity, there is no satellite constellation. So in the case of general relativity, it took 100 years. So it's really long-term investment. If you stop investing in the long term, well, there will be less short-term development in the nearby future. So it's really a matter of reaching a balance. Not saying that all should go to fundamental research. We also need applied research and engineering and immediate deployment. But one feeds the other, and the other cannot continue to grow progress if the applied research does not exist, and the same goes, applied research will not continue to develop if fundamental research does not continue. So it's really a question, is progress good? And when you see that we managed to get a vaccine against a pandemic in a few months, I would say that yes, progress is good. Black Plague killed 30% of the population in the Middle Age.
Thank you.
Thank you. So quick question. So does space debris pose a similar problem?
For us astronomers, no, because they're too small. Okay, really roughly speaking, anything smaller than 1 meter for us is faint, and anything smaller than half a meter is virtually undetectable, unless you track them. But for our astronomy telescope, it's not an issue. However, space debris are a problem because space debris can cause more debris and more collisions. So it's not a question for astronomy; it's a question for the rocket scientists.
Mm-hmm. Thank you.
Another live question about tracking the position of these constellations. So would the NORAD LTE database be useful to feed the predictive and scheduling tools to track the constellations?
Oh yeah, but yes, but actually in the case of these constellations, these satellites are extremely aware of their position. And one of the reasons is that they have to, the current generation, those that have been launched now, are equipped with lasers to have communication from satellite to satellite with lasers. So that means that they need to know their position at a few centimeters. The exact precision is commercially classified, but Starlink is ready to give us their position at meter. So that means that we know where they are, and so that means that we don't need NORAD to measure them. The constellations are feeding their orbital elements directly to the relevant databases. And yeah, and really to track individual ones for us is probably not the simplest way to go. It's simpler to put a camera.
Okay, and questions. I'm going to summarize one of the questions from an amateur astrophotograph. His work, his pictures are ruined by the satellite constellations. So the question will be, do you take into consideration the amateur astronomers?
Okay. Amateur astronomer, please contact me. I would love to talk to you because it's hard to get real good data from small telescope. I can easily get data from a net meter. For me, it's much more difficult to get data from a 20 centimeters. So it really depends on many factors. The aperture, the field of view, the sensitivity. And basically, if it's a good telescope, wide field, sensitive, amateurs will be affected. The number of trails really scales only with the field of view, which means that a good amateur telescope will have the same field of view as the Vera Rubin telescope, which means that 20% of their early evening exposures are going to be affected.
Thank you.
Now, will the trail be visible? I don't know. And that's where I would really love to receive an email from said amateur astronomer. Is that you, Chris Badele?
Yes.
Yes. Okay. I copy the email. Sorry, too many screens.
No worries. No worries. We have the same issue. Well, Olivier, thank you again for being with us today. It was a very nice talk. Thank you for all the information, and also thank you for taking the time to advertise for amateur astronomers and all of that. So thank you very much.
Pleasure. And again, don't panic, but it's serious. But we are on it.
We got the message. So we have just a brief announcement. So again, as you all now know, we have the IAU junior member photo competition. So don't hesitate to participate. We select a winner every month. So you can see all junior members can participate, and you can submit your picture on the following this link here. So again, thanks everyone for joining us. Thank you, Olivier. And if we receive other questions, we will try to answer them in writing. We also want to advertise the next event will be on Thursday, April 29. It will be on, so it's Dr. Richard Scalzo from the University of Sydney. We'll talk about quantifying and managing uncertainty. And so it's going to be on from 9 a.m. to 10 a.m. on the Australian Eastern Time, or 7 a.m. to 8 a.m. Australian Western Time. So it's a completely different time zone for us. But again, so thank you very much all for being here. Thank you for taking part to this discourse. And again, thank you, Olivier, for your talk.
Thank you so much, Olivier. Thank you. Bye to all of you.
Thank you, guys. Bye.
Bye.
Bye.